All right, so let's get started. Uh, First of all, hello and welcome everyone to the second week of interactive live sessions for the course on fundamentals of convective heat transfer, which is being offered by NPTEL. The course is currently being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering, IIT Guwahati. My name is Debjit. I am currently a PMRF scholar at IIT Madras, and every week we shall be solving some problems together and having a 2 hour long interaction. So I'll be the way it will work is I have prepared some questions of my own. We will be first of all solving them together. So you will read the question carefully and figure out the solution. And once you have done so, you can either unmute and answer or you can type it in the chat box. If you have any doubts regarding it, we can always discuss. And apart from this, anything related to the course material, you can bring it up during these sessions, and we can have an open discussion about it. So the main purpose of these sessions is to have a two-way interaction. The lectures are, you know, unidirectional. It goes from the professor directly towards you. You don't have a way to give feedback, or if you want to make sure that you are understanding correctly or not, there's no way to do that. So that's where these sessions come in. So let's try to participate actively in it and make it a success. Okay, so without any further ado, we will jump into the first question of today's session. So this is question number one, which is asking us that Reynolds transport formulation can be applied to what? There are four options given below. Option A, any property. Option B, any path function. Option C, both A and B. Or is it option D, none of the above? So once you have figured out the correct solution, you can once you have figured out the correct solution, you can either type it in the chat box or you can unmute and answer. Okay, so read the question carefully. Question number one of today's session. So Reynolds transport formulation can be applied to what? Is it option A, any property? Option B, any path function? Option C, both A and B? Or is it option D, none of the above? Okay, let me once make sure that I am properly visible and audible. Can anyone let me know?
Yes, sir.
Okay, thanks. So this is the first question of today's session. It's asking us that Reynolds transport formulation can be applied to what? Is it option A, any property? Option B, any function, any path function, sorry. Or is it option C, both A and B? Or is it option D, none of the above? If you have any doubt regarding the question, you can always ask. And once you have figured out the solution, you can either type it in the chat box or unmute and answer. It's up to you. So the second week of lectures consisted of some preliminary ideas, one of them being sorry, one of them being boundary layers, the another one being the conservation equations of energy, and we brushed up a little bit on conservation energy of momentum, conservation equation of momentum as well, which is also known as the Navier-Stokes equations. For solving problems related to convective heat transfer, we will be needing those preliminary concepts again and again. So the second week was just to set the stage for the future uh, concepts that we will be learning. So one of the basic fundamentals over there is Reynolds transport theorem, which actually connects any any system law to a control volume. So as we can understand that in a fluid system, in a fluid flow configuration, the concept of a system becomes really problematic. There, the concept of a control volume becomes much more useful. So that's where Reynolds transport theorem comes in, since all the laws of physics that we know, they are in a system domain. So in order to translate them from the system domain to a control volume domain, Reynolds transport theorem comes into the picture. So now this question, the question number 1 of today's session, is related to that Reynolds transport theorem. It is asking us whether it can, to what quantities can it be applied to. Is it option A, any property? Option B, any path function? Option C, both A and B, that is any property as well as any path function? Or is it option D, none of the above? I would urge everyone to participate in this. I don't see any responses here. See, there's no need to be afraid or feel shy. Like, it doesn't matter whether you get the answer wrong or not. Uh, we are here to learn, so it's just a learning process. But in order to do that successfully, you need to participate in this. Okay, so let's see, let's have some responses. Okay, we have one response in favor of option A, any property. We have one response in favor of option A. Let's see, let's get some other answers. We have one response, okay, second response in favor of option C, both A and B. Another one in favor of option C. Yes, Girdhar Singh, you have any question? You can unmute and ask. Girdhar Singh, you have raised your hand. Do you have a question? Feel free to ask. Okay, so we have four responses now in favor of option C and only one response in favor of option A. Let's see what others have to say. Let's get some more responses. Come on. Okay, another one in favor of option C. So we have five responses in favor of option C and one in favor of option A. So question number 1 of today's session is that Reynolds transport formulation can be applied to what? Is it option A, any property? Option B, any path function? Option C, both A and B? Or is it option D, none of the above? We have once you have figured out the correct answer to this, you can type it in the chat box or you can unmute and answer. And if you have any doubt regarding the question, you can ask away. No need to hesitate. So let's see, are we getting any more responses? Let's have a look at the solution then. So we have one response in favor of option A and many others in favor of option C. Now, unfortunately, or rather fortunately for that one person who answered in favor of option A, Reynolds transport formulation can be applied for properties only, not for path functions. So let's say What is a path function? A work is a path function. Now, Reynolds transport theorem can't be applied to work as such. We can apply it on energy, uh, which is a property, and that property will be conserved in a, control volume, something like this. So that's why option C, which says both properties as well as path functions, won't be correct. It would be just properties. So what are the properties which can be applied uh, to Reynolds, or on which properties can Reynolds transfer theorem be applied? It can be mass. In that case, the formula that we get is continuity equation. Then it can be momentum, which is again a property. Then we will get the Navier-Stokes equations. It can be energy. In that case, similarly, you will get energy conservation equations. It can be the concentration of certain species as well. You get the gist, right? Any kind of a property, we can apply Reynolds transport theorem to it. Yes, anyone has any question?
Sir, what is last property?
Species. So let's say you have a mixture of some methane and oxygen, which you are trying to mix properly. Then you will ignite it, and you will get some combustion, and something which happens within an engine. Let's say. So in that case, uh, we let's say this is the domain. In this case, the concentration of CO2, or sorry, not CO2, concentration of CH4 or methane, it would be different in different locations, right? So let's say if I call it CH4, then CH4 will be a function of x, y, and t of both space and time. So in that case, the concentration of CH4 as well as the concentration of O2, these will be conserved as well. So these are also a property, concentration of that species. Am I making sense?
Yes. Sir, please explain Reynolds transport formulation.
Okay, Reynolds transfer formulation. So that is basically, let's say, uh, first of all, it would be difficult to derive it entirely. It suggests you go through some, fluid mechanics lectures on the derivation of Reynolds transport theorem. But I will briefly outline what it does. Is that, let's say I have any property n. In that case, dou n dou t of a system would be equal to the integral of, let's say, some rho v into, now dou n dou v would be some intrinsic property n. So if n is the extensive property, small n would be the intrinsic property. Then something like this. So dou dou t of this. Sorry, let me write this down a bit more correctly. Over a control volume plus, this would be, okay, here again rho would be there, and once again rho into divergence of v and n dot dA, whatever, over the control surface. So apart from getting into the math of it, what it tells is that if there is a control volume like this, and there is a flow, let's say with v in, there is a flow out of it, v out, and that flow is carrying some property n with it. Now, in that case, the rate of change of uh, that property in case of a system would be given by this dou n dou t for a system, and when we translate it to a control volume, that would be given by the right hand side of this equation. We usually have laws of physics which tells us what this dou n dou t of a system would be. So let's say if n is mass, dou m dou t would be 0 because mass cannot be created or destroyed. That is the one of the fundamental laws of mass conservation. In case of momentum, the rate of change of momentum would be equal to the sum of all the forces acting on it. So that way we will get the left hand side of the equation, and the right hand side of the equation we will solve that to you know get more ideas about the how small n is distributed as a function of space and time. We solve for it. So this is how Reynolds transfer theorem comes to help us. Is it clear what I just said?
Yes, sir.
Thank you. Any other questions? Anyone? Okay. So if there are no questions, we will move on to the next question of today's session, question number 2, which is asking us that after boundary layer approximations are made for flow over a flat plate along x-axis, consider the following statements and mark the statement which is false. So I have a flat plate like this. I have a velocity u infinity coming towards it, uniform velocity profile. Now, as we know that when it encounters this solid surface, a boundary layer, a hydrodynamic boundary layer would be formed. Now, in that case, there are several approximations which we make while deriving, doing a scale analysis and other analysis of a boundary layer. So once all those approximations have been made, consider the following statements and mark the statement which is false, not true. So there are four options. In between them, some of them may be false. You have to pick that one out. So option A is saying dou p dou y is equal to 0. Dou p dou y is equal to 0. So along x I'm taking my free stream velocity and y is the direction normal to that flat plate. So in that case, is it option A, dou p dou y is it equal to 0? Option B, continuity equation unaffected. Option C, x momentum equation becomes parabolic in nature. Or is it option D, none of the above? So read the question carefully, and once you figure out the correct solution, you can type in the chat box or you can unmute and answer. If you have any doubts regarding the question, you can ask that as well. Okay, we have one answer in favor of option B. Let's wait for everyone to respond. So we have two responses in favor of option B, one in favor of option C, one in favor of option D. Let's see. Our audience is a little bit divided this time. Let's see what everyone has to say. There's no hurry. Take your time and try to figure this out. Another response in favor of option B. Another one in favor of option B. Option B seems to be the popular choice this time. So this is question number 2 of today's session, which is asking us that after boundary layer approximations for flow over a flat plate along x-axis, consider the following statements and mark the statement which is false, incorrect. So is it option A, dou P dou I equal to 0, option B, continuity equation unaffected, which got one more response, option C, which is saying x momentum equation becomes parabolic in nature, or option D, none of the above. With 5 plus 2, 7 responses so far. Let's see if we get some more. So question number 2 of today's session, it's asking us, after boundary layer approximations for flow over a flat plate along x-axis, consider the following statements and mark the statement which is false. Is it option A, dou P dou I equal to 0? Option B, continuity equation remains unaffected? Option C, x momentum equation becomes parabolic in nature? Or is it option D, none of the above? We have received 5 responses in favor of option B so far, and options C and D has gotten 1 each. So once you have figured out the correct solution, you can type in the chat box or you can unmute and answer as well. So let's have a look at the solution. The solution is option D, none of the above. So all of these equations, all of these statements are in fact correct. That's why option D would be the correct solution. So let's go through them one by one. Uh, if we go through the lectures, we can see that dou P dou Y is actually becomes very, very low than dou P dou X. That's why it's ignored. So it's basically dou P dou I is approximated close to 0. So that's why option A would be correct. Now, continuity equation, it remains unaffected. So dou U dou X plus dou V dou Y is equal to 0. So we have done scale analysis over here. We can scale U as U infinity, X as L, which is the length of the plate, and Y as delta. So that would give us U infinity by L plus the scale of V we do not know. So this is the scale of it, and it should be equal to V by delta. Now, why should it be equal? Because there are only two terms over here, and the sum of them is equal to 0. So, when do we get the sum of two numbers equal to 0? So, let's say I have a plus b equal to 0. When do we get that? When a is equal to minus b. Now, it can't happen that one of these terms can be ignored and still we will get 0. So, that would mean in a trivial case a equal to b equal to 0. So that doesn't happen. We know that this dou u dou x is scales as u infinity by L, which is a finite number, which does not go to 0. So that's why both these terms will stay. And as a result, continuity equation will remain unaffected. Then the third one, x momentum equation becomes parabolic in nature. So then again, we using the help of scale analysis, we have seen that uh, dou to u dou y square is much greater than dou to u dou x square. So that's why we put this equal to 0 in the Navier-Stokes equation. Then we finally get dou u dou x plus uh, v dou u dou y is equal to nu into dou to u dou y square. This equation becomes parabolic in nature. So option C is also correct. So since these three statements are correct, none of them are false. So the correct answer to this particular question, which is asking us to pick out a false statement, would be actually option D, none of the above. Does that make sense? Any questions regarding this one? Any questions, any doubts? Would you like to challenge it? Any remarks you have to make? Please feel free to do so. So everyone understood, right? Why option D would be the correct one and not B, which was the popular choice.
Sir, why U infinity upon L is proportional to V upon delta, where negative sign?
Sorry.
Sir, in continuity equation affected.
Yeah.
Uh, sir, why U infinity upon L is proportional to V upon del, and where negative sign?
Yeah, see, negative sign would come if I try to directly solve this equation. That's not what we do in scale analysis. In scale analysis, what we do is we just look at the order of magnitude of the different terms. Sorry. So in this equation, for this particular term, I know that it scales as u infinity by L, and dou v dou I know that it should scale as v over delta. We don't know the scale of v yet. So from this, we will infer that scale of v should be equal to u infinity into delta by L. Now, I'm not saying the exact value, whether it will be positive or negative. I just know that the order of magnitude will be like this. So if I say that I have u infinity equal to 10 meters per second, then I have L equal to, let's say, 1 meter, and delta is equal to 1 millimeter, or I can write this down as 10 to the power minus 3 meter. So if this is the scenario, then I can say that my vertical velocity v would scale as it would scale as u infinity, that is 10 meters per second, into delta, that is 10 to the power minus 3, over L, which is 1. So this comes out around 10 to the power minus 2 meters per second. So this does not mean that the vertical velocity v has to be exactly this 10 to the power minus 2. It can be 1 into 10 to the power minus 2. It can be 2 into 10 to the power minus 2. It can be 9.78 into 10 to the power minus 2. You get my point, right? It could be minus as well. It can be plus as well. I don't get that particular information out of it, but the only information I get is it would be of the order of 10 to the power minus 2 meters per second.
Okay, sir.
Okay. Any other questions? Good. This was a very good question. Like, why is it not negative then? So that would depend on how these velocity gradients are. So if dou u dou x is negative, then dou v dou I would be positive, right? For that we have to solve for u, and for doing that the continuity equation is not enough alone. We need to solve the Navier-Stokes equations as well. This one within the boundary layer. Once we have gotten u, then we can plug in here and see what dou u dou x would look like, whether it will be positive or negative. Then we will get that, okay, so dou v dou y must be negative of that. Okay.
Yes, sir.
Any other questions? Any other doubts regarding this one or anything else related to this? No, right? Okay. So then we will move on. We'll move along to question number 3 of today's session, which is asking us the ratio of momentum diffusivity to thermal diffusivity is called what? Is it option A, Prandtl number? Is it option B, Nusselt number? Is it option B, Biot number? Or is it option D, Grashof number? So these are all non-dimensional numbers, as we know, or sorry, dimensionless numbers. Among these, what is the ratio of momentum diffusivity to thermal diffusivity known as? Let's see, we have two answers in favor of option A, Prandtl number. 3. Okay. No need to hurry. Read the question carefully, and once you have figured out the solution, you can type in the chat box. Okay, another response in favor of option A. Another one. Option A seems to be the popular option this time. Another one. So 6 responses in favor of option A. Very quick responses this time. We got 6 responses so far and all in favor of option A. 1, 2, 3, 4, 5, 6. Yeah. Anyone would like to argue something else? So the ratio of momentum diffusivity to thermal diffusivity is called what? Is it option A, Prandtl number, option B, Nusselt number, option C, Biot number, or is it option D, Grashof number? Excuse me a little bit. So, do we get any more responses? The ratio of momentum diffusivity okay, another one in favor of option A. No one seems to contradict over thermal diffusivity. So, what is momentum diffusivity? Can anyone tell? What is another name by which we call momentum diffusivity? Okay, we have another response in favor of option A. Quite the popular one. Now, so this should be easy, right? What is momentum diffusivity? I need one answer. At least one answer, if not multiple. Kinematic viscosity, someone wrote in the chat box. So, kinematic viscosity also, which is the Greek symbol that we use to uh, denote it. It's nu, right? Which is equal to mu over density. This is the kinematic viscosity. And what is the Greek letter which we use to denote thermal diffusivity? Alpha, correct. Alpha is given by K over rho Cp, where K is the conductivity, thermal conductivity, Rho is density as we know it, and Cp is the uh, heat capacity of the material, specific heat capacity rather, right? So the ratio which I have in hand is this nu over alpha, which everyone is telling it's equal to Prandtl number. Let's have a look at the solution. It is indeed Prandtl number. So this was a no-brainer, pretty easy. Uh, I guess no one has any questions regarding this one. Anyway, if you have, please go ahead and ask. This was a very simple one. Uh, if there are no questions, we will move along. We'll move on to question number 4 of today's session. Now, this is a numerical type question. So, bring out your calculators if you need so, or, keep a pen and paper ready. So, for flow of fluid over a heated plate, the following fluid properties are known. Dynamic viscosity is equal to 0.001 Pascal second. Specific heat at constant pressure is equal to 1 kilojoule per kg Kelvin. Thermal conductivity is equal to 1 watt per meter Kelvin. The hydrodynamic boundary layer thickness at a specified location is 1 millimeter. Sorry. The thermal boundary layer thickness at the same location in millimeter is what? Is it option A 0.001? Is it option B 0.01? Option C 1? Or is it option D 1000? So no need to hurry. Take your time and try to figure out the correct solution. So for flow of fluid over a heated plate, the following fluid properties are known. Dynamic viscosity is equal to 0.001 Pascal second. Specific heat at constant pressure is 1 kilojoule per kg Kelvin. The thermal conductivity is 1 watt per meter Kelvin. The hydrodynamic boundary layer thickness at a specified location on the plate is 1 millimeter. At that same location, what would be the thermal boundary layer thickness? We have two responses in favor of option C, that is equal to 1. Another one in favor of option C. C. Lot of answers in favor of option C. Okay, so as someone has remarked in the chat box that as Prandtl number equal to 1, both thicknesses will be the same. So let's have a look at the solution. Everyone is indeed correct. The correct solution would be option C, that is 1. So, and the process was correct as well. So the Prandtl number is equal to nu by alpha as we saw in the previous question. So I can find out nu as uh, let's say 0. Okay, here. Uh, So I can write this down as mu over rho, and alpha I can write down as k over rho Cp. So rho would cancel out, and I'll get mu Cp by k. The value of mu is given as 0.001. The value of Cp is given as 1000, that is 1 kilojoule, and k is equal to 1. So ultimately I'll get Prandtl number equal to 1. And as you know that delta over delta t, this is a function of Prandtl number to the power m. Now m could be anything, it could be half or one third depending on the value of Prandtl number itself. But anyway, since it's 1, 1 to the power anything would be equal to 1. So that's why delta would be equal to delta t. Delta is given as 1 millimeter. As a result, delta T, the thermal boundary layer thickness, will also be 1 millimeter. Correct. Very good. So that's why option C would be the correct answer. Any questions regarding this one? Any questions, any doubts, any remarks? No, right? Everything is clear? So we will move on. We'll move on to question number 5 of today's session, which is telling us this is once again a bit numerical, but you won't need a calculator for this. Uh, so the non-dimensional fluid temperature profile near the surface of a convectively cooled plate is given by so and so, where y is measured perpendicular to the plate, L is the plate length, and a0, A1, and A2 are arbitrary constants. Now, if TW and T infinity are wall and ambient temperatures respectively, if the thermal conductivity of the fluid is K and the wall heat flux is Q double prime, then the Nusselt number is equal to what? Is it A0? Option A. Option B, A1. Option C, 2A2. Or is it option D, A1 plus 2A2? No need to rush. Try to understand the question after reading it carefully and then try to figure out the correct solution. If there is any part of the question which is not clear, feel free to ask. Okay, we have one answer in favor of option C, 2A2. Let's see what others have to say. Okay, we have another response in favor of option B, that is A1. Another response in favor of option B. Take your time, there's no hurry, but try to do it correctly. So, we have received three responses so far, two in favor of option B and one in favor of option C. I would urge everyone to, try your hand at this and come up with a solution. It doesn't matter if it's wrong, but it's important that you try. So the question is, the non-dimensional fluid temperature profile near the surface of a convectively cooled flat plate is given by this: Tw minus T divided by Tw minus T infinity is equal to A0 plus A1 y over L plus A2 y over L whole square, where y is measured perpendicular to the plate, L is the plate length, and A0, A1, A2 are arbitrary constants. Now this Tw and T infinity are wall and ambient temperatures respectively. If the thermal conductivity of the fluid is K and the wall heat flux is Q double prime, then what is the Nusselt number? Is it option A, A0, option B, A1, option C, A2, option C, 2A2, or is it option D, A1 plus 2A2? If anyone is facing any problem doing this or solving this, you can unmute and ask. We can, you know, work through whatever problem that you're facing. Only three responses so far. Others, are you trying or uh, trying and facing any problem is okay, but not trying isn't. So these are the type of questions which will be given in assignments as well as in the final exam as well. So if you become well versed with these types of questions, then uh, those examinations or assignments won't be a problem at all. All right, so let's have a look at the solution. The solution is option B, A1, as some of you have correctly figured out. So, how did you reach there? What was the path that you took? Your answer was correct, option B, A1, but what was the method that you followed to reach there? So, what is the problem? We have a flat plate like this. It's at temperature TW. There is flow over it. Let's say at some U infinity and temperature T infinity. There is this one hydrodynamic boundary layer, one thermal boundary layer. Now, the temperature, if I plot it as a function of y, x and y, so let's say this is my y axis. If I plot the temperature like this, it's TW over here, it's some T infinity over here, and it would follow something like this, given that T infinity is less than TW, right? Now, this profile, it's given in a different way, that TW minus T over TW minus T infinity is equal to some A0 plus A1 y over L plus A2 y over L whole square. I have to find out what the Nusselt number is equal to. So what is the Nusselt number in the first place? We can write this as uh, you know h into TW minus T infinity divided by k into dou t dou y at y equal to 0, right? Is this correct? So from here, I can write down t as, so this will be multiplied this way, then subtracted from tw minus tw into t infinity multiplied by this thing, a0 plus a1 y over l plus a2 y over l whole square. Okay, so then if I try to do dou t dou y, then this becomes 0 minus tw over t infinity. This is getting differentiated by y now, so this becomes 0. This becomes a1 over l. This becomes a2 by l square into 2y. If I compute this at y equal to 0, then this y goes to 0. As a result, this goes to 0 as well. So finally, I'll get minus of tw minus t infinity into a1 over l. Now, we'll try to compute this Nusselt number once again. So this will be h into tw minus t infinity divided by k into minus of tw minus t infinity a1 over l. This and this cancels out. Uh, these things remain, right? HL and K. Am I making any mistake over here? Can someone help me? I don't see any mistake over to find new. The denominator should have negative sign. Okay, that I can take care of. So this is negative. This way, this negative doesn't show up. What about the rest of it? Any suggestions, anyone?
Sir, how to zero a2 square upon L square into y?
So this one, I have a0 into a1 into y over L plus a2 into y by L whole square. Now I'm differentiating this with respect to y. So t becomes dou t dou y, tw becomes 0. This is a constant, it will stay as it is. Uh, a0 is a constant, so if I differentiate with y, it becomes 0. Then this one is a1 over L into y. Differentiating y gives me 1. And this one a2 by L square. I'm keeping it as a constant. And I have y square, which differentiating with y, I'm getting 2y. Now I'm computing this at y equal to 0 at the wall. So that's why I'll put y equal to 0. As a result, this term goes to 0 and I'm getting this. So let's try to do this in a little bit different way, the computation of the Nusselt number. So I have this as of now, and there is this wall heat flux Q double prime. Let's compute that. That is equal to minus K into dou T dou Y, right? We figured out that dou T dou Y is this. So this should be minus K into minus of TW minus T infinity multiplied by, sorry, multiplied by A1 over L. So these things cancel out, K into T infinity, TW minus T infinity, A1 over L. Now I'll write down this Nusselt number as uh, Q double prime into L by K. This is one way of writing Nusselt number, right? So now if I include this value of Q double prime, this one, then it will be, sorry, not this, it will be divided by delta T. So K delta T in the denominator and K delta T by L. Yeah. So this is the convective heat transfer. Let me write it down properly. So this is the convective heat transfer divided by the conductive heat transfer, which is K into delta T by L. So this becomes, so L by K comes over here. Delta T is nothing but TW minus T infinity. And now we will substitute this value of Q double prime over here. So it will be K into A1 over L into TW minus T infinity. Yeah. So this will cancel out, this will cancel out, and only A1 would remain. So that's how B would be the correct answer. Sorry, I took some time to do this. I couldn't figure it out initially. There any questions or doubts regarding this question? Anyone, anything? If there are no questions, then we will move on. We'll move on to question number 6 of today's session, which is asking us which of the following non-dimensional quantities are involved in non-dimensional energy equation. Is it okay? So there are then four numbers listed here: one Reynolds number, two Nusselt number, three Prandtl number, four Eckert number. And then it's asking us which of these four will be involved in the non-dimensional energy equation. Is it option A 1, 2 and 3? Is it option B 1, 3 and 4? Option C only 3 or option D only 1? Okay, we have one answer in favor of option B. It says 1, 3 and 4. That is Reynolds number, Prandtl number and Eckert number. We have another response in favor of option A, another one in favor of option B. Let's see what others have to say. Another one in favor of option B. Okay, someone is changing their answer to option A. So two each. Which one will win? A 2, B also 2. That's fine. Okay, another one in favor of option A. So A is leading now, 3-2. So option A means 1, 2 and 3. That is Reynolds number, Nusselt number and Prandtl number. And option B is 1, 3 and 4. That is Reynolds number, Prandtl number and Eckert number. Let's see, any more responses? So we are solving question number 6 of today's session, which is asking us which of the following non-dimensional quantities are involved in the non-dimensional energy equation. Is it option? Okay, then there are four numbers given listed here. That is one Reynolds number, two Nusselt number, three Prandtl number, and four Eckert number. Then we have different combinations in the options given below. So option A is 1, 2, and 3. Option B is 1, 3, and 4. Option C only 3. And option D only 1. We have received 5 responses so far, 3 in favor of option A and 2 in favor of option B. Can we get some more responses?
Sir, please do fast.
Okay, someone is in a hurry then. Okay, we'll move along. So let's have a look at the solution. The solution is option B, 1, 3, and 4. So it's Reynolds number, Nusselt number, sorry, not Nusselt number, Prandtl number, and Eckert number. So as it turns out, Nusselt number is not there. How is it so? It's the energy equation. It should be there, right? So let's try to do this. So the energy equation, I'll write it in one dimension only. So it will be something like this, equal to that will be T by rho Cp here. I won't write in terms of energy. So energy means enthalpy, right? We can write this as rho Cpt. We have this over here. This is the pressure differential. This is the viscous dissipation term. And we will have the heat diffusion term given by this. Right. So now let's non-dimensionalize it. So for temperature, we can use something like this, which we have seen earlier. We will call this theta. Then for temperature scale, we will use this. Then theta would be T by. So non-dimensional temperature, we will write in this way. Non-dimensional velocity, we will write as U over U infinity. Then non-dimensional pressure, we will write as pressure over uh, rho U infinity squared. Then, okay, let's for a second forget about the viscous dissipation term. And yeah, so these are the things which you have, right? Okay, so x star would be x over L. With this, we can start solving for it. So first of all, let's write down this thing. So dou theta, okay, time also we have to non-dimensionalize. Let's say we do t u infinity over L. So this would be, let's call it tau instead of t star. So dou tau plus u star dou theta dou x star. I'll send this rho Cp on this side. So it will be 1 by rho Cp over here, whatever we write down later. And k by rho Cp, we will get alpha. and into this thing. Other terms will also come here. So let's see. Let's do the first term first. So t we are converting to theta. So for that will be uh, so dou theta would be dou t divided by this thing. So dou t would be dou theta multiplied by that. And similarly, t would be tau into L by u infinity. Give me a second. Okay, cool. So this takes care of these terms. Then dou p dou t. In this case, p would be rho u infinity square into p. So I'll have a rho infinity squared over here, and the rest of this stuff would be inside. So dou p star dou tau plus u star into dou p star dou x star. Plus we have alpha into this. There will be some other terms also coming out of it. So on the numerator we have dou t star uh, dou square t. So there will be one this thing over here and x star in below. So x would be L into x star. So this is x star squared. This will be L squared. So now let's try to simplify this. So on this side we have dou theta dou tau. I'm writing this as a total differential just to simplify this. So over here we have u infinity square by Cp into 1 u infinity comes here, one temperature difference as well, and there's a L over here. Plus what we have here. So this term will get cancelled. This is what we have from earlier. Now we are bringing these terms over this side. So it will be u infinity so this comes out to be the Eckert number into dou p dou tau and this thing we can simplify it as 1 over Reynolds number into Prandtl number into the double derivative of the non-dimensional temperature. So Reynolds number shows up, Prandtl number shows up, and the Eckert number shows up as well. But however, the okay, one L will also get cancelled over here. So these are the three non-dimensional numbers that show up, but Nusselt number does not. So that's why option B would be the correct answer. Any comments from anyone? Any questions? Any doubts? Okay. So if there are no questions, we will move along. We'll move along to question number 7 of today's session, which is asking us for flow of viscous fluid over a flat plate. If the fluid temperature is same as the plate temperature, the thermal boundary layer is what? Is it option A, thinner than the velocity boundary layer? Option B, thicker than the velocity boundary layer? Option C, of the same thickness as the velocity boundary layer? Or option D, not formed at all? Read the question carefully, and if you have figured out the correct answer, then type it in the chat box. So this is the case where T1 is equal to T infinity.
Here, 2 lakh.
So option, we have one answer in favor of option D, not formed at all. Let's see what others have to say. Another one. So what happens in this case? Is it option A, thinner than the velocity boundary layer, thicker than the velocity boundary layer, of the same thickness as the velocity boundary layer, or is it option D, not formed at all? We have three responses in favor of option D. Any other responses? It's a very simple question. We will have a look at the solution. Those who chose option D were correct. The the thermal boundary layer is not formed at all. Why is it so? What is the reason? Can anyone answer? What is the reason? Why is it not formed at all?
Sir, thermal boundary layer is formed due to temperature difference, but here no temperature difference, so
Correct.
not formed.
So since there is no temperature difference, so first of all, we have to visualize what a boundary layer actually is, be it thermal or hydrodynamic. So uh, if in the wall there is some temperature, and as a result that heat would flow either in or out into the fluid, and as a result it will try to reduce the difference between that of the wall material and that of the fluid. So if it's less, then this will be the kind of the boundary layer, or if it's higher, then this will be the kind of boundary layer that forms. But in case where there is no difference, like it's T infinity over here as well as T infinity over here, the temperature profile would be straight, right? So there will be no effect that the wall has, that the boundary has on the fluid. So there is no layer formation as well. So what a layer means is that the boundary has some effect on, or some influence within the fluid domain. So the region of influence, that's what we call a boundary layer in the first place. So since there will be no heat flux, there won't be any influence over the temperature. So that's why there is no formation of boundary layer at all. It's a simple question, but you have to be conceptually strong about this one. So good, very good. Now we will move on to the last question of today's session, which is asking us, when are the laminar boundary layer equations not valid? Is it option A, when Reynolds number is very large? Is it option B, turbulent flow? Is it option C, beyond separation point? Or is it option D, both B and C? Question number 8 of today's session. This is the last question, which is asking us when are the laminar boundary layer equations not valid? Is it an option A, Reynolds number very large, option B, turbulent flow, option C, beyond the separation point, or is it D, both B and C? We have one response in favor of option D, both B and C. Another response in favor of option D. Sorry.
Excuse me, sir.
Yes.
Sir, for the option A and B,
Mhm.
sir, is it that they are having the same meaning? The Reynolds number is very large and the flow will be also a turbulent one.
I see your confusion, but that's not really the case. In boundary layers, the flow remains laminar even until Reynolds number to the power, let's say 10 to the power 5. This is pretty high, but still not turbulent for flow over a flat plate.
Yes.
That's where I'm separating this option A and option B.
Yes, sir. That lead to the confusion. Yes.
Yeah, yeah. I
Yes.
understand. It's a bit ambiguous over there. Uh, Okay, so let's have a look at the solution. The solution is indeed option D, both B and C. So for turbulent flow, laminar boundary layer equations won't be effective. There is something called turbulent boundary layer theory. You can, you know, search it in Google and see. It's a bit advanced concept, but it's different from laminar boundary layers. And beyond the separation point, then there is also a wake formation. So over there also the standard boundary layer equations they don't follow. But for a very large Reynolds number, up to the level of 10 to the power 5, laminar boundary layer equations they hold true. So that's why option A won't be the correct answer, but option B and C are both correct. As a result, you have to pick option D, which says both B and C.
Sir, all options are right.
All options are right. No, option B and C are correct. So that's why option D would be the correct one. Okay. So that's all for today from my side. If you have any questions, feel free to ask.
So which type of questions can we ask in final exam?
Exactly like this. So if you keep attending these interactive live sessions and as well as the assignment questions, so uh, you know, union of two Venn diagrams, these live session questions and the assignment questions, that would be the type of questions asked in the NSEM or the final exam, whatever you call it. Okay.
Sir, same question can we ask?
Probability is low, but I don't know. I don't set those questions, so I can't guarantee you that I won't repeat it. Someone else will set those questions. It's up to them.
Yes, thank you, sir.
Yeah, okay. So this is one of the initial classes. So I guess it will be great to get to know each other. So I'll start by introducing myself. So as I already said, my name is Debjit, and I'm currently doing my PhD in IIT Madras. Prior to that, I did my BTech in mechanical engineering from Kolkata in Jadavpur University. So I'm currently, working on pulmonary fluid mechanics, which is the fluid mechanics within the lung. So, and apart from that, fluid mechanics and heat transfer are, pretty favorite subjects of mine. So I enjoy studying these and discussing these with as many people as possible. So that's my background. Now, it would be great if you guys introduce yourself one by one and let us know a bit about your background and, most importantly, why you're trying to learn this course on convective heat transfer. Because this is a bit of an advanced course. This is not a run of the mill heat transfer course which we do in undergrad. So you guys can raise your hands and go one by one just to get to know each other. We will be having these discussions for 10 more weeks from now on. Anyone would like to volunteer themselves? Yeah, so Prashant Patumkar, you can.
Yes, very,
Yeah.
very good evening, sir.
Yes.
Myself, Prashant Patunkar.
Hmm.
I am working as a faculty member in Mechanical Engineering Department at MIT EDT University in Pune.
Okay.
I completed my graduation in Mechanical Engineering from College of Engineering, Aurangabad,
CET.
and
CET, right?
College of Engineering from Aurangabad in
Okay.
Maharashtra.
Okay. Okay. Yes, I have heard
Mm,
about it.
Yes, yes. And I completed my master's from IIT Bombay in the
Oh, nice.
specialization of thermal and fluids engineering.
Nice.
And I am currently pursuing my PhD as well.
Okay.
My domain of working is the evaporative cooling.
Oh, awesome.
Yes, yes. And I am interested to learn this course to upgrade the knowledge and to learn from best of the best teachers, obviously from the IITs.
Awesome.
Yeah, yes. Thank you, sir.
Okay. So let's keep meeting every week. Anyone else would like to go? You can raise your hand and then unmute and speak up. No need to feel shy. Come on. You can just say your name and then why you're interested in learning this course. That would be enough. Anyone else? Please raise your hands. If you feel like, if talking is a bit of a problem, then you can type in the chat box as well as you feel like.
Sir, myself, Brajen Singh.
Hi, Brajan.
I have joined this course for credit in our college.
Okay.
Because this
So,
is mandatory in our college.
okay, so you can transfer these credits, right? Great.
Yes, yes.
Which college are you studying in?
Sir, Madan Mohan Malviya University of Technology, Gorakhpur.
Gorakhpur, okay. You're doing masters now, is it?
No, sir, BTech
BTech, BTech, okay. Which year are you
graduations.
in now?
In third years, mechanical engineering.
Okay. So, but this will be a bit of an advanced course for you. Have you taken any course on heat transfer or fluid mechanics earlier?
No, sir.
Fluid mechanics you haven't taken? You're a third year student, right?
Sir, I studied the fluid mechanics in college, no, but not from NPTEL.
No, no, I'm not telling NPTEL. It's not that NPTEL is the only way you can learn it. Doing any course is enough. So you did fluid
Yes,
mechanics
yes,
earlier, right? Okay, great.
yes, sir, yes.
Any course
And
on
heat transfer
heat transfer as well?
is in this semester.
Okay, good,
Yes, sir.
good. So in this course, you will learn, specifically convective heat transfer in a more detailed manner.
Yes, sir.
Okay, great. Thanks, Brajendra.
Okay. Thank you. Welcome, sir.
Okay, anyone else?
Sir, can we left now?
Yeah, yeah, sure. It's up to you. I won't force you to stay. Okay, so Suraj Kumar is telling that my name is Suraj Kumar Gupta and currently pursuing BTech from. Oh, so you guys are batchmates, right? Suraj and Brajendra?
Yes, sir. Here all are my batchmates except Sir Dr. Prasant, sir.
Okay,
All are my batchmates.
okay, awesome. Okay, so see you guys next week. This time in this same meeting, we'll have another fruitful discussion. Hopefully, today was really great. So thank you for that.
Yes, thank you, sir.
Okay, so I'll close this session. Bye bye. Good night.
Good night, sir.